October 2009. Out in the Arizona desert, a convoy of heavily camouflaged GM pickup trucks thundered across miles of punishing terrain. Dust clouds stretched behind them. Suspension components slammed into hidden rocks. Temperatures climbed well past 100 degrees. Every vibration, every jump, every full throttle pull was pushing one question to its limit. Could General Motors build a truck engine powerful enough to stand toe-to-toe with Ford's growing off-road empire? Most people think the battle between GM and Ford was all about badges and brand loyalty. They picture flashy commercials, horsepower wars, and heated debates between truck owners. But what almost nobody knows is that beneath the hood, engineers were fighting an entirely different war. It wasn't just about making more power. It was about building an engine that could survive punishment most street vehicles would never experience. And what happened next changed the future of GM's full-size trucks. By the late 2000s, Ford had already begun reshaping the high-performance truck market. The first-generation F-150 Raptor was unlike anything buyers had seen before. It wasn't simply another pickup with aggressive styling. It was designed to attack rough terrain at speeds that would destroy an ordinary truck. Long travel suspension, reinforced chassis components, massive tires, and eventually a 6.2-liter Boss V8 transformed the Raptor into an icon almost overnight. GM couldn't ignore what was happening. Silverado and Sierra had always been respected for towing, durability, and everyday capability. They sold in huge numbers and built loyal followings across North America. But enthusiasts were beginning to ask an uncomfortable question. Where was Chevrolet's answer to the Raptor? At the center of that challenge sat one engine, the 6.2-liter V8. To many people, it was simply another big displacement truck engine, reliable, powerful, familiar. But underneath that ordinary reputation was one of the most sophisticated small-block V8s General Motors had ever installed in a production pickup. The legendary Chevrolet small-block V8 had already become one of the most successful engine families in automotive history. Since 1955, its compact pushrod design had powered everything from family sedans to championship-winning race cars. Instead of chasing overhead camshafts like many competitors, Chevrolet engineers kept refining the overhead valve layout. The design stayed physically smaller, weighed less than many rival V8s, and produced enormous low-end torque, exactly what truck buyers demanded. Generation after generation, the formula improved. Then came the Gen IV family. This wasn't merely an updated version of an old engine. Nearly every major component had evolved. Stronger aluminum blocks appeared in premium applications. Deep skirt block architecture dramatically increased rigidity. 6-bolt main bearing caps reduced crankshaft movement under heavy loads. Improved cylinder heads increased airflow while maintaining combustion efficiency. One version stood above the rest, the 6.2-liter variant. Known internally through engine codes like L92 and later L9H, it displaced 6,162 cubic centimeters, or 376 cubic inches. Its dimensions were carefully chosen. A 4.065-inch bore paired with a relatively short 3.622-inch stroke allowed the engine to breathe exceptionally well at higher RPM while still delivering the kind of torque truck owners expected. Compression ratios reached as high as 10.5, one in early versions. Impressive for a naturally aspirated truck engine designed to run on premium pump fuel. Factory output immediately caught attention. Early versions produced around 403 horsepower and 417 pound-feet of torque. Later developments pushed those numbers even higher, eventually reaching 420 horsepower and 460 pound-feet in Ecotec 3 form. Those weren't just impressive specifications on paper. They translated into effortless acceleration, confident towing, and remarkable flexibility across the rev range. But horsepower numbers never tell the whole story. The real challenge wasn't making 400 horsepower for a few seconds. The real challenge was making that power every single day while towing 10,000-pound trailers, climbing mountain grades in the summer heat, idling through construction zones, and then surviving another 200,000 miles without falling apart. That's where the engineering became fascinating. Instead of abandoning the traditional pushrod architecture, GM doubled down on it. A single camshaft remained buried inside the block, operating 2 valves per cylinder through hydraulic roller lifters, pushrods, and rocker arms. Critics often dismissed the layout as outdated compared to Ford's overhead cam engines. Yet the pushrod design kept the engine physically compact, lowered its center of gravity, reduced moving parts, and allowed engineers to package more displacement into less space under the hood. It was old-school thinking refined with modern technology. Lightweight aluminum cylinder heads improved heat dissipation, electronic throttle control sharpened responsiveness, sequential multi-port fuel injection optimized fuel delivery under varying loads. Advanced engine management constantly adjusted ignition timing based on NOx sensors, air temperature, throttle position, and dozens of other inputs every second. Everything seemed to be coming together. Then Ford raised the stakes. When the Raptor entered the market, it wasn't just selling horsepower, it was selling an image: Baja racing, desert jumps, factory-backed toughness. It convinced buyers that an off-road truck could be as exciting as a muscle car. GM suddenly found itself chasing more than performance figures. It was chasing perception. Engineers knew the 6.2-liter had the strength. They believed it had the durability. On paper, its naturally aspirated V8 offered instant throttle response that many enthusiasts actually preferred over turbocharged rivals. But proving that to customers would require thousands of hours of brutal testing, constant refinement, and solutions to problems that were only beginning to reveal themselves. Because hidden beneath all that power were weaknesses almost nobody outside General Motors knew existed, and fixing those weaknesses would become the toughest challenge of all. By the time the 6.2-liter V8 reached production, GM engineers knew they weren't simply building another truck engine. Expectations had changed. Buyers wanted the towing ability of a heavy-duty pickup, the acceleration of a muscle car, and the reliability to rack up hundreds of thousands of miles. Delivering all three at once was a far bigger challenge than most people realized. At the heart of the engine sat one of GM's greatest strengths, the Gen IV small block architecture. While Ford continued developing large overhead cam V8s, Chevrolet stayed committed to its compact pushrod philosophy. Some critics dismissed it as old technology. GM's engineers saw it differently. Fewer moving parts meant less weight, a lower engine height, and more room under the hood. That packaging advantage also allowed easier servicing and a lower center of gravity, both of which benefited truck handling. The block itself was built with deep skirt construction, wrapping farther around the crankshaft than older small blocks. 6-bolt main bearing caps held the forged steel crankshaft securely under heavy loads, reducing flex during high RPM operation and towing. Aluminum versions of the block helped trim significant weight compared to traditional cast iron, while maintaining excellent structural rigidity. Its dimensions told another important story. The engine displaced 376 cubic inches, or 6,162 cubic centimeters, using a 4.065-inch bore and a 3.622-inch stroke. That relatively over-square design allowed the pistons to travel a shorter distance with each revolution, reducing average piston speed and helping the engine rev more freely. Combined with large rectangular port aluminum cylinder heads, airflow improved dramatically over previous truck V8s. Compression remained relatively aggressive for a naturally aspirated production truck engine. Early versions ran 0.5, 1 compression, while later EcoTech 3 variants increased that to around 11.5, 1 thanks to direct fuel injection. More efficient combustion meant more power from every drop of fuel without sacrificing durability. On paper, the numbers looked impressive. The original L92 produced approximately 403 horsepower at 5,700 revolutions per minute and 417 pound-feet of torque at 4,300 revolutions per minute. Later L9H and L86 variants improved calibration, breathing, and fuel delivery. By 2014, the L86 EcoTech 3 generated 420 horsepower at 5,600 revolutions per minute and 460 pound-feet of torque at 4,100 revolutions per minute. That output placed GM's naturally aspirated V8 among the strongest half-ton truck engines on the market. Performance backed up those figures. A properly equipped Silverado with the 6.2 could sprint from 0 to 60 in roughly 6 seconds, remarkable for a full-size pickup weighing well over 5,000 pounds. Quarter-mile times landed in the mid-14-second range at nearly 100 miles per hour. Towing capacity exceeded 12,000 pounds in certain configurations, while payload ratings remained highly competitive, but raw numbers only told part of the story. The real battle was happening inside the engine. Generating more than 400 horsepower while hauling heavy loads created tremendous heat, oil temperatures climbed, cylinder pressures increased, bearings experienced enormous stress every time the throttle stayed pinned, climbing a long grade with a trailer attached. GM's engineers spent thousands of hours validating cooling performance under extreme conditions. Larger coolant passages improved heat transfer around the combustion chambers, while piston oil squirters sprayed pressurized oil onto the underside of each piston crown. That simple addition dramatically reduced piston temperatures during sustained heavy operation and minimized the risk of detonation under high load. It was an elegant solution, but another problem was waiting. Fuel economy regulations were tightening across North America. Customers still wanted big V8 power, yet governments demanded lower emissions and improved efficiency. Engineers needed a way to satisfy both. Their answer became one of the engine's most controversial technologies: active fuel management. Under light throttle, hydraulic lifters collapsed on 4 cylinders, allowing the engine to operate as a V4. In theory, it was brilliant. Highway fuel economy improved noticeably, and emissions dropped without forcing buyers to give up V8 performance when they needed it. In practice, the system proved far more complicated. Over time, some AFM lifters failed to unlock correctly. Drivers reported ticking noises, rough idle, misfires, and illuminated check engine lights. In severe cases, a collapsed lifter could damage the camshaft itself, requiring expensive repairs. Some engines also developed excessive oil consumption as oil entered the combustion chamber during repeated cylinder deactivation cycles. Independent mechanics began seeing familiar patterns. Valve lifters stuck. Camshaft lobes wore prematurely. Metal particles circulated through the oiling system. Repairs often required removing cylinder heads and replacing multiple internal components, a labor-intensive job that frustrated many owners. GM continued revising lifter designs, software calibrations, oil deflectors, and PCV systems over successive model years. Later engines generally proved more reliable, but the reputation of early AFM-equipped trucks lingered for years. And then another revolution arrived. For the 2014 model year, the 6.2-liter entered the Ecotec 3 generation. Instead of relying solely on port fuel injection, engineers introduced high-pressure direct injection operating at more than 2,000 psi. Fuel was sprayed directly into each combustion chamber, cooling the incoming air charge and allowing higher compression without destructive knock. Variable valve timing optimized camshaft position throughout the RPM range, improving both low-end torque and high-speed breathing. The result was immediate. Throttle response sharpened, torque delivery became smoother, fuel economy improved despite the increase in horsepower. Owners could tow heavy trailers during the week and enjoy muscle car-like acceleration on the weekend without feeling like they were driving 2 different vehicles. Ford, however, wasn't standing still. The second-generation Raptor abandoned its naturally aspirated 6.2-liter Boss V8 in favor of a twin-turbocharged 3.5-liter EcoBoost V6. On paper, it produced even more torque, 510 pound-feet, and delivered it much earlier in the rev range. Many believe turbocharging represented the future. GM chose a different path. Instead of chasing boost, Chevrolet trusted displacement, instant throttle response, linear power delivery, the unmistakable sound of a naturally aspirated V8 climbing toward redline. For many truck enthusiasts, that experience couldn't be replaced by turbochargers, regardless of the numbers. The rivalry had evolved beyond horsepower charts. It had become a battle between 2 completely different engineering philosophies. And that battle would shape the future of American performance trucks for years to come. In the end, The winner wouldn't be decided by dyno sheets alone, it would be decided by the drivers who demanded power, durability, and character every time they turned the key. By the middle of the 2010, the battle had reached its peak. Every new truck launch felt like another round in a heavyweight championship. Ford was promoting turbocharged technology as the future. Ram was pushing more torque than ever before. And Chevrolet was putting its faith in something that had defined American performance for generations. A naturally aspirated V8 that relied on displacement, precision engineering, and proven durability instead of forced induction. The 6.2-liter became the flagship engine in the Silverado High Country, GMC Sierra Denali, and later the luxurious GMC Yukon Denali, Cadillac Escalade, and Chevrolet Tahoe High Country. It wasn't reserved for stripped-down work trucks. It powered the vehicles that represented the very best GM had to offer, and customers noticed. Independent testing consistently placed 6.2 equipped Silverados among the quickest full-size pickups on the market. A properly configured Silverado 1500 could accelerate from 0 to 60 miles per hour in about 5.8 to 6.2 seconds, depending on the model year and drivetrain. Quarter-mile runs landed in the mid-14-second range at nearly 100 mile-per-hour, performance numbers that would have embarrassed many V8 muscle cars from just 2 decades earlier. But acceleration wasn't what made the engine special. It was the way it delivered that power. Touch the throttle at just 1,500 revolutions per minute, and the engine responded instantly. There was no waiting for boost to build, no complicated turbo plumbing, just a deep growl, immediate torque, and smooth acceleration all the way to its 5,800 revolutions per minute redline. With 460 pound-feet of torque available, towing a heavy trailer up a steep mountain pass felt effortless. The engine never sounded strained, it simply dug in and kept pulling. For truck owners, that confidence mattered more than flashy horsepower figures. The 10-speed automatic transmission, introduced on later models, made the combination even stronger. Co-developed by GM and Ford, the transmission kept the 6.2 operating in its sweet spot more often, improving acceleration, towing performance, and highway fuel economy. Ironically, even as the companies fiercely competed in showrooms, they quietly collaborated on one of the most advanced truck transmissions of its time. Still, the rivalry wasn't one-sided. Ford's second-generation Raptor arrived with its twin-turbocharged 3.5-liter EcoBoost V6, producing 450 horsepower and an impressive 510 pound-feet of torque. It accelerated harder at lower RPM and excelled in high-speed desert driving. For many buyers, it represented the future of performance trucks. GM responded in a different way. Rather than building a direct Raptor competitor immediately, Chevrolet focused on refining the entire truck platform. The 6.2 continued evolving, with improved software, stronger internal components, and more sophisticated engine management. When the Silverado ZR2 finally arrived, the proven 6.2-liter became its heartbeat. Paired with Multimatic DSSV spool valve dampers, locking differentials, skid plates, and 33-inch off-road tires, it gave Chevrolet a serious factory-built off-road truck capable of challenging the Raptor in rugged terrain while maintaining excellent everyday drivability. But just as the engine reached its greatest level of refinement, a different kind of pressure began closing in. Global emission standards became stricter almost every year. Governments demanded lower carbon emissions, fuel economy regulations tightened, manufacturers started investing billions into hybrid systems, turbocharged downsized engines, and eventually fully electric trucks. The era of the big naturally aspirated V8 was slowly coming to an end. GM adapted by introducing dynamic fuel management, a far more advanced successor to active fuel management. Instead of switching between 8 cylinders and 4, the system could operate using multiple cylinder combinations depending on engine load. Combined with automatic stop-start technology and increasingly sophisticated engine control software, it squeezed more efficiency from the familiar small-block architecture without sacrificing its signature character. Even so, enthusiasts remained divided. Some appreciated the improved technology. Others preferred the simplicity of earlier V8s without cylinder deactivation or additional electronic complexity. Entire aftermarket industries emerged offering upgraded lifters, performance camshafts, tuning solutions, and AFM delete kits for owners seeking maximum reliability and traditional V8 behavior. That's one of the greatest compliments an engine can receive. People weren't trying to replace it. They were investing thousands of dollars to keep it alive. The aftermarket embraced the platform with open arms. Cold air intake systems, long tube headers, performance camshafts, ported cylinder heads, upgraded valve springs, and custom ECU tuning regularly pushed naturally aspirated output well beyond 500 horsepower. Add a supercharger from companies like Magnuson or Whipple, and the same basic 6.2 architecture could reliably produce 650, 700, or even over 800 horsepower with the right supporting modifications. That speaks volumes about the engine's foundation. Its deep skirt block, robust rotating assembly, efficient cylinder heads, and decades of small block evolution gave builders enormous confidence. Whether powering a daily driven Silverado, an Escalade, or a dedicated performance project, the engine proved remarkably adaptable. Today, the 6.2-liter remains one of the last great naturally aspirated American truck V8s still available in mass production. While much of the automotive industry has embraced smaller turbocharged engines and electrification, this engine continues to represent a philosophy that values instant throttle response, mechanical simplicity, and effortless torque over complexity. Did it defeat Ford's Raptor? Not exactly. The Raptor carved out its own identity as the benchmark for factory high-speed off-road trucks. Chevrolet chose a different path, using the 6.2-liter to create trucks that balance performance, refinement, towing capability, and everyday usability. Instead of chasing the Raptor in every category, GM built an engine that earned respect for its versatility and unmistakable V8 character. And maybe that's the real story. This wasn't an engine designed to dominate one race or win one comparison test. It was built to start every morning, haul heavy loads, survive brutal conditions, and still put a smile on the driver's face every time the throttle hit the floor. In a world rapidly moving toward downsized turbocharged engines and electric powertrains, that kind of engineering has become increasingly rare. So the next time you hear the deep rumble of a Chevrolet 6.2-liter V8, remember what you're really listening to. Not just another truck engine, but the result of more than half a century of small block evolution, a machine that proved old-school engineering could still compete in a rapidly changing world. If you enjoyed this deep dive, let me know in the comments which legendary truck engine you want to see next. Should we uncover the story behind Ford's Boss 6.2, Ram's legendary 5.7 Hemi, or another forgotten American V8 that changed automotive history? And if you don't want to miss the next documentary, make sure to subscribe, because there are plenty more incredible engine stories waiting to be told.